Gerken in 2006 and in 2010 did some studies with artificial language that demonstrate this kind of Bayesian reasoning process that we've been talking about. And the idea, basically, is that infants are trained on data from an artificial language which consisted of words that followed a certain pattern. These are the data D in our sort of Bayesian inference reasoning here. The data D that they were given followed a certain pattern. And the idea was to determine, if you're the infant, which generalization describes the pattern for words of that artificial language, the more specific hypothesis or the more general hypothesis, which in this case is a superset of the more specific hypothesis. And so originally, many years earlier, Marcus and colleagues had found that very young infants will notice that words made up of 3 syllables follow a pattern that can be represented as AAB or ABA. That is a repetition of some kind with a third element. And you can abstract, if you are an infant, this kind of rule from specific examples. So that's the kind of setup that Gerken used. So the A syllables, for example, would be things like lay and we, and the B syllables might be things like D and J. So you can make these patterns of lay D or we J if you're in, say, the AAB language, and vice versa if you're in the ABA language. And that's the idea. These are the data you're getting, and that is the kind of generalization that infants of a certain age are capable of doing. So what Gerken did is says, okay, let me construct these kinds of patterns. So for example, we're going to focus here on the AAB language words, but she also did it with the ABA language words just to make sure there wasn't anything special about this particular formation of the rule. But AAB patterns would be things like lele D, lele J, we D, we J, right? Following a certain pattern where you repeat the first syllable and then have a new third syllable, right? That's your basic pattern. And so the question then was simply, what kind of generalization would children make if they were given particular kinds of data from these same artificial languages that Marcus and colleagues found infants are capable of making generalizations about? Like, what do they do when you have certain scenarios? And so the idea would be, let's say you have 4 syllables out of which you can construct your AAB patterns. Here's your A syllables and here are your B syllables. And so the idea is infants only see a subset of the language, right? And you have to generalize based on that subset to the appropriate hypothesis that accounts for words of that language. So the training in the experimental condition, which is really the locus of activity here, was where you would have 4 word types that are consistent both with the more specific, the less general hypothesis of repeat the first syllable and then follow it by the syllable D, or the more general hypothesis where you repeat the first syllable and just have it followed by another syllable. So lele D, we D, GGD, D. These are compatible with both, right? Both repeat the first one and follow it by that one syllable D, or repeat the first one and follow it by some syllable, which in this case always happens to be D. And so the control condition, when this is really just to make sure that they can, in fact, make the same generalization Marcus and colleagues found they could, was train on ones that are only compatible with the superset, with a more general hypothesis. So lele D, we J, GG Li, de Wei, right? Train on these, and this is the only one they're compatible with. So the control condition is basically used to see what children's behavior is, or infants really. When the data are only consistent with one of the generalizations, are they capable of actually performing the way we would expect them to if they made a generalization? And so in this control condition would be because you want to make sure kids can actually do your experiment. If the kids fail to make the generalization in the control condition, then the results in the experimental condition are not going to be that informative because you can't tell what they're doing if they can't even pass this basic one where what they should be doing. They should be forming this more general AAB style generalization. Oh, there we go. So let's see what they did. So this is using a head-turn preference procedure, which is a sort of task where you're really looking to see how long children are interested in a new stimulus based on how long they look at it, more or less. It's an attention kind of mechanism. And the details are not super important for our purposes, but simply just we're going to be talking about time that children spend looking, right? And this is with 9-month-olds. So in the control condition, they hear these stimuli that are only compatible with the more general hypothesis for about 2 minutes, right? And then the test is like, okay, now let's give you 2 stimuli, one which follows that pattern, but not with syllables you heard, with new syllables, or one that doesn't follow that pattern. So for example, if you use syllables ko and ba, you want to test in your test koko ba versus ko ba ko, and you've been hearing stuff with lays and we's and g's and days, right? New syllables, but same pattern. So the behavior is that if children learn the more general pattern, then they're going to prefer to listen to something that follows that pattern with new exciting syllables over a word that doesn't, right? They're going to prefer koko ba, which follows that AAB pattern, koko ba, over ko ba ko, if they form that generalization. And that's exactly what they did. They listened longer on average to test items that were consistent with that pattern as opposed to items that weren't, right? So good, they're able to form that generalization. We take this to mean that they can notice that pattern when the data support it and make it from this artificial language data. 9-month-olds can handle this. Great. So, in fact, in some follow-up work in the recent years suggests it might be pretty easy for infants because it's a familiarity preference. They have to look longer at the familiar thing as opposed to a novelty preference. And in general, the idea is that when you have a familiarity preference and you look at the familiar thing, that's because it's a little easier and a little less exciting. Anyway, the experimental condition now really is the question. So let's look now at our training data, which are now consistent with two hypotheses. The more specific one, the less general one, where you have repeat that first syllable and follow it by the syllable D, and also that more general one we had before. And so the behavior, what do we expect? Well, if they learn the more general pattern, then we expect the same thing. If we give them new syllables, they're going to prefer that AAB pattern over something that doesn't follow it, koko ba over ko ba ko, right? But what happens if they prefer the less general pattern, or they just fail completely? Then they're not going to have a preference, right? They're not really going to know what to do with this because this doesn't really speak, doesn't really refer to the rule that they internalized or failed to internalize if they didn't infer anything at all. And that's pretty much what they found. When you give them data that are consistent with both, they do not prefer something that follows that pattern over something that doesn't. So they're not making that generalization, okay? But what are they doing? They either learn the less general one or nothing at all. And how can you tell the difference? Well, you want to swap up your test items. So now you're going to train them the same way, but this time you're going to test them on things that either follow the more specific one, koko D, say, versus things that don't. So if they learn that less general pattern, now they're going to prefer koko D over ko D ko. And if they didn't, then they'll again have no preference. So what did they do? Okay, so now they prefer koko D. Okay, so it seems like given this ambiguous data that are compatible with both our more specific and our more general hypothesis, they are in fact behaving as if they make that more specific general hypothesis, the idea that they go with, that generalization. So this means, given ambiguous data, they make the less general hypothesis, less general generalization, hypothesis 1 there, just like a Bayesian learner would. So we can now remind ourselves why this is, which basically is that here is your setup, right? You've got your actual data, which are these 4 items, right? And you've got 16 total words in your language that you can generate that are going to be compatible with that more general hypothesis, right? And so it all comes down to likelihoods, right? So if these are your 4 data, these in fact are the only 4 data that can be generated. So the probability of generating each one is just 1 out of 4, right? And we're just going to focus on the ones in the data intake. So we just have these 4 that we're generating, right? Versus if you're generating it from hypothesis 2, well, you have 16 things you could have picked from. So that's a 1 out of 16. You multiply that 4 times and you get a much smaller number, right? So it's our likelihood that's doing the work. You have this big difference where the subset hypothesis, the smaller one, the more specific one, has a higher likelihood of generating these data than the larger one. And if we assume the hypotheses are equally complex a priori, we don't have any bias towards one or the other, and there are 2 of them, so they each get like a probability of 1/2, then when we do our Bayesian calculation, the posteriors really just reflect this huge difference in the likelihoods, right? We prefer the more specific one because it is more probable for generating these data than the more general one. And that's really what's doing our work. So, it's the likelihood